Right, we should get started. We only have an hour for 4 excellent speakers, so I won't take too much time on the introduction. But welcome to the space weather session. We're calling this an emerging application, even though we have space weather applications from a GSM. Should we take our seats? Yes, even though we have the old spectral, the GSM model in a whole atmosphere model, and we are providing space weather products from that at the Space Weather Prediction Center. It's actually not in the UFS formally because it's not part of FE3 and it hasn't got all the CCPP physics. And we'll be hearing more about the development of that from Kevin's talk in the second talk this afternoon. But before that, I'd like to welcome Fabrizio Sassi. He's now at NASA, so to give us a NASA perspective for how they're going to hopefully extend the GEOS into the higher altitudes. Fabrizio.
Thank you for, I should try to finish on time or even before so that there is room for questions. So this presentation is just an introduction to some ideas that we are floating around at Goddard Space Flight Center on extending the GEOS model to higher altitudes. And although I'm the face of this project, this could not happen without the help of my colleagues, Stephen Pawson, the head of GMAO, and Ruth Lieberman, my colleague in the ITM lab. And what better way to start to talk about whole atmosphere modeling than this figure from a Thomas Immel paper, where he showed a clear connection between the lower atmospheric weather in the form of non-migrating tides and the brightness of the ionosphere. But nothing happens. Nothing happens. Oh, there you go. So you're controlling? Oh, the 2 side arrows? Okay. Okay. So what is whole atmosphere modeling? I'm sure that this is a question that anybody in this room can answer, but I just wanted to provide an introduction. Whole atmosphere modeling started in the late 1990s here in Boulder at Anchor when Ray Robel proposed to couple the CCM-3, at that time the state-of-the-art community climate model of Anchor, with the time GCM, and demonstrated that there is weather that is propagating from the lower altitudes to the upper levels. And a prime demonstration of this was shown for stratospheric warmings, and the seminal paper by Hanley and Ray Robel showed that, in fact, there is an upward influence of the anomalies generated by the strat warming towards the thermosphere and ionosphere. Not only that, but even Hanley and myself showed that there is a downward influence with anomalies of winds that start at higher altitude and influence the lower atmosphere. To make a long story short, a lot of things happened in the last 20 years. NOAA, NRL, Anchor have made huge progresses. NASA, instead, has been absent. But we need a whole atmosphere model, which essentially is defined a model from the ground to space, to make efficient, and this is probably a NASA bias, an efficient use of observation and models that the heliophysics community wants and needs to use. We need to replace the silos with a whole Earth system view in which observations are used on equal footing as observations of precipitation in the troposphere. And we need to have this model to address important questions of, in short-term, medium-term, and long-term timescales. Okay. Nothing happens. Oh, there you go. Okay. So it's the up and down arrows. What's the current state of the art of all atmosphere modeling? There are two aspects. One is the nudging technique, which I am guilty of having used for a long time. And in that sense, you use a weather model, and you think that whatever you're generating from below propagates upwards, and with appropriate boundary conditions at the top, you try to model the upper atmosphere. In that sense, the upper atmosphere is, you're not using observations in the upper atmosphere, but you're assuming that everything is the word that comes to my brain is slaved, but I was warned not to use that word. So, current state of the art, more recently, is the involvement and the introduction of data simulation systems that leverage both meteorological observations from the lower atmosphere and data simulation in the upper atmosphere, so what we call heliophysics missions. This is something that ANCHOR is doing with the WACAM-X DART system, and in this sense, you're using the observations in the upper atmosphere, and you inform the upper atmosphere what is happening at that during your simulations. So what are the key science drivers that we are using that are the motivation for this work at Goddard? One motivation is a natural disaster. So we have seen what happened with Tonga, and before that Krakatoa and Pinatubo. There are prominent examples. But remaining with Tonga, we know that there are large bite-outs of ionospheric densities during this volcanic eruption. But also, from a climate perspective, there was an injection of 58,000 Olympic-sized pools in the atmosphere, and this figure you see at the bottom is from MERA, and it's the water vapor at the equator. And you can see that after Tonga, the amount of water vapor increases, but because age of air in the stratosphere is very long, we are still dealing with these pools of water in the lower stratosphere. So it's not just an event that is short-lived, it lasts for a long time. Space traffic is something that NASA is very interested in. According to Morgan & Stanley, the space industry will grow to revenues of about $1 trillion by 2040. And clearly, that's an important important revenue. But also, there are aspects of pollution. All these rocket launches may inject pollutants from the exhaust, and current studies indicate that the effect on ozone layer is limited. However, this is based on the current space traffic. By 2040, it is expected in this Morgan & Stanley report that we will have daily launches, intercontinental daily launches. So, things are going to change. So we need to move away from, again, silos and look at a coupled physics of a system of systems in which you connect the magnetosphere, you connect the ionosphere, and you connect with the thermosphere, because these processes is a cascade of events that start off with a geoeffective solar storm and goes down to changing the densities in the lower thermosphere. Space weather, then, is very important for NASA, not only because of the space flight opportunity that we are going to have in the next 10 years, but, the aurora is the visible effect of magnetosphere-ionosphere coupling. There are important efforts that are being carried out now with the Center of Geospace Storm, and I know that people here in the room are involved in that project. That is a very interesting project, and in fact, I look forward to learn more about that and work with those folks. It's important because one aspect that I learned the hard way with the different whole atmosphere models that I've used in the past is that energetic input from the sun can be very disruptive of your numerics in your model. And the way you deal with them is still an open question, unless you're willing to go to time steps that are untenable under a second. So what we have is some challenges and opportunities. The the thing I want to emphasize, and the thing that I keep emphasizing with NASA, is that the integration of heliophysics observations with the Earth system modeling and data simulation that is currently going on at NASA is an economical and effective way, to advance understanding of the upper atmosphere, because the alternative is just to put more spacecrafts in orbit, but that is very expensive, and that takes a decade. In fact, we are not going to have probably observations for the upper atmosphere for another decade. I'm thinking of dynamic and GDC. But at the same time, there are opportunities like this paper by Nicholas Dietrich, in which he shows that just by using ionospheric observations, in particular in this case, RO GPS electron densities, they are able to reduce the root mean square error in neutral properties. To me, this is groundbreaking. To me, this is very interesting. Obviously, more research needs to be done because this is done with the time GCM. This is done in a very idealistic context. I think this was an Aussie study. The point here is that this result demonstrated that the potential benefit of having a very tightly coupled system in which we use both ionospheric and a few atmospheric observations that we have to make advances. And now, nothing happens. There you go. Why do we want to do it at NASA? Very briefly, again, the motivation is that the heliophysics community has a suite of many upper atmospheric observations that they have their own value in the way they have been utilized up to this point, but they can be utilized also for applications in the context of a whole atmosphere model. We have the GEOS system, which is capable of representing key drivers of the upper atmospheric variability, but also something that is very interesting to me, it values each observation in the context of multiple other observations. So no matter what your observation is, whether it is precipitation in a troposphere or electron density at 500 kilometers or 300 kilometers, they're treated equally. This opens the possibility for a vertical extension of GEOS and create a framework for Earth observations to be used, and opens the possibility for research and for synergies with other agencies like NOAA. And obviously the main ultimate goal for NASA is to support the spaceflight opportunities. How do we do that? Very briefly, how much time do I have left? She says 1. 4 minutes, okay. Total, okay. I'll try to wrap it up quickly. So what we want to do is to take GEOS, which currently has a lead at 80 kilometers and is valid up to 60 kilometers. And with the careful introduction of upper atmospheric observations, specifically SABRE, and eventually also wind observations, we want to extend the validity to what we call the MLT region, and leveraging the efforts that are currently going on with the GCSDA, the development of the new data simulation framework, bring all the observations together and create a ground-to-space reanalysis that is coupled with MERA-2. Then we will extend it to higher altitude, and the ultimate overall goal is to combine all these disparate efforts that are currently going on, even at Goddard itself, but in general in the community, and capitalize on the success of each one component. The ultimate aspirational goal is to have a whole atmosphere capability that includes also space weather drivers and physics. This is a very busy slide. Basically, this is saying that our goal is to develop extramural synergies with NOAA, with CGS, produce a breakthrough science, and support NASA space flight opportunities. This is another way to say that this project, if we get it off the ground, will be staged and eventually, so it's not going to happen in a year or two, it's going to happen over several years. And we are looking forward to work with other partners, including NOAA, and especially with NOAA because we share the same dynamical core, we share the same, probably the same physics, and probably also the same model coupling. And I leave it at there, and I'll take questions.
Great. Thanks, Fabrizio. Yeah, we've got time for a couple of quick questions. Anybody? So the dynamical core that you're using, the FV3 dynamical core, the same as NOAA, is that
Yes.
the plan? Okay. Do you have a particular sort of use case that's the main emphasis of this development, or is it fairly broad still?
It's still fairly broad. It's still, we still need to decide specifically how this system will be utilized. The main short-term goal is to create this reanalysis from ground to space for the past 20 years.
Okay, and trying to improve the lower atmospheric dynamics as well as the upper atmosphere,
Correct.
as the focus is on the upper,
Right.
so it's both the whole atmosphere.
Correct.
Any questions? Yeah, Hanli.
So in your roadmap, you have a stage that midterm step that goes to a 350. Why is there, why not just what stops you from going to MLT from MLT to the?
Yeah, no. In the hurry to finish the talk ahead of time, I skipped some important statements. Don't take any of these numbers to be actual levels where we will stop the model development. It's just a figure of merit. I think that if you can go to up about the FPIC, you can still kind of get away from having a fully coupled ionosphere and include also magnetospheric inputs. If you go to the exobase, then you have to have the whole thing coupled together. There is no other way. So it's some sort of altitude where we can still, up to about the FPIC, we can still consider mostly driven by dynamics.
Thanks a lot, Fabrizio. It's great. Yeah, now I'd like to invite Kevin Viner. He's the main developer for the FV3 WAM. We're trying to migrate from the GSM WAM to the FV3 WAM, and Kevin is the main developer at EMC.
Excellent. Thank you, Tim. So what I'm going to talk about today is primarily some of the technical details in the neutral atmosphere extension of FV3. This is collaborative work between EMC and the Space Weather Prediction Center. And this is the team that I've been working with for, well, about 1.5 years now. So the system that's currently in operations is the global spectral model version of the WAM, the whole atmosphere model, and the ionosphere plasmasphere electrodynamics model on the ionosphere side. Get my animation going. So what I'm mainly going to talk about today is the WAM model and replacing that with FV3. So right now, we're going 0 to 600 kilometers at about 2-degree resolution. It's hydrostatic, 150 levels, and it's a version of the old GFS. So it's got ozone, chemistry and transport, cloud physics, hydrology, radiation, of course. And it uses the WAM data assimilation scheme. So we've got a couple of concerns if we want to do this ionospheric modeling, right? You've got the solar and geomagnetic activities coming from above, and then we've got the concerns of the lower atmosphere coming from below. We've got the tides, we've got the planetary and gravity waves coming up and forcing things from below. As far as the IPE that we're coupling to, it's a time-dependent global 3D model from 90 kilometers to several Earth radii, and it uses ESMF to do the coupling and the 3D regridding. So in terms of the WAM IPE products and concerns at SWPC, they're concerned about high-frequency communications. They're concerned about positioning, navigation, timing, and other communications, as well as things like satellite drag. And I'm not going to dive into that too much. I will defer to Tim on any questions on the IPE. So what are some of the goals of upgrading to the FV3 WAM? We want to get the non-hydrostatic effects. Eventually, we'd like to get the deep atmosphere effects. We have the potential to go to much higher resolution than 2 degrees. But primarily, we need the unification with other NOAA models under the UFS umbrella, which means the FV3 DICOR and CCPP for the physics. So if you've been here all week, I'm going to beat a dead horse. FV3, what is it? It's finite volume on a cube sphere. It's non-hydrostatic. Linen-Rude 2D finite volume advection. Special feature I'll get into a little bit is it uses Lagrangian, floating Lagrangian vertical pressure coordinate. It's currently shallow atmosphere approximation. It uses a forward and time split explicit stepping. And it has a semi-implicit solver for vertical that should just say sound waves. It doesn't have it for gravity waves. CCPP, I'm sure a lot of you have heard about. This is used for all the UFS physics packages, and it's no different for the WAM. So some of the things we've had to build in to FV3, first one is multi-gas functionality. We have to worry about the change in composition of the atmosphere once we get above 100 kilometers. So we have tracers for molecular and atomic oxygen and molecular nitrogen, and that changes your, well, formerly constants, your gas constants. So as you see here in these equations, now we have to sum over these various gases to get those values correct. And we have to be very careful when converting between potential temperature and temperature. Next, we have to worry about the high atmosphere physics. So what we've done thus far is take the IDEA physics package from the GSM WAM used at SWPC, and that's been ported to a single scheme thus far in CCPP. So it's one large scheme. This is a snippet of the XML file, the suite file for CCPP, where you see in red just the WAM phys, as we call it. Kappa correction. So one of the things you have to revisit now that we're changing composition is what have we neglected in most of our tropospheric modeling? And it's this term in red here that says, I need a time-dependent change in composition term in my thermodynamic equation. So what we've done thus far is we've added this kappa as an advective tracer whose value is reset at each step by the change in composition to compute this term. One thing I want to dive in a bit more, because this is something I've worked on in detail, is the horizontal molecular diffusion. So right now, this is treated fully explicitly. The coefficients are computed in the physics, and then we apply limiters to make sure that we're not violating the stability limit. It's done in a time split fashion after each acoustic step in the solver. However, there are some issues with this. One of them is that since we have a floating Lagrangian coordinate, those levels may be warped by gravity waves and advection. We would prefer to have nice, smooth isobaric surfaces if we can. Number two is that the way FV3 works is there's a splitting between the tracer transport and the dynamics. Which means if we're applying this on the inner acoustic steps, we're not getting the tracers right. So at the moment, one thing we have to do is do the tracers in line with the dynamics, which costs more. It's not ideal. So in the future, we'd like to group some of these things together in a more cohesive module that's done implicitly, either on the remapping steps or on the physics time steps. Sticking with molecular diffusion, which really is incredibly important once you get above 100 kilometers. We had to add vertical molecular viscosity of vertical velocity, because that's not a variable that exists inside the physics. So we have to apply it fully implicitly, and we do that inside the vertical semi-implicit solver of the dicore, just by adding this red term. So we discretize this fully implicitly and solve a tridiagonal system for W, and that manages to stabilize things. So I'm going to show some early results from our work. The setup for that experiment is C96, so it's just 1 degree grid spacing. We're using 150 levels starting at 500 kilometers. And I'm going to show results from a single 5-day forecast that's initialized from remapping from the GSM WAM initial conditions. And we're going to look at global mean values of temperature and composition. And we're going to compare with the GSM WAM and the empirical NRL MSIS model. And the goal is we want to approximately match the skill, or not the skill, match the results. So here on the left, we're looking at a global temperature profile up to 400 kilometers at 24 hours, and on the right, out to 5 days. In blue, we've got the GSM WAM result. In the dashed line, we have MSIS, and in red, we have the FV3 WAM. And what you see is that at 24 hours, they match pretty closely, and that at 5 days, we were a bit warmer than MSIS with the GSM WAM, and we're closer to MSIS with the FV3 WAM. But they're all fairly similar. In terms of composition, here we're looking at the left at atomic oxygen at 5 days, and on the right, molecular oxygen at 5 days. And once again, we have the FE3 WAM and the GSM WAM looking very similar. So to conclude, I would say we are approximately matching the results of the neutral atmosphere GSM WAM model using the UFS-FV3 version. We'd like to begin testing at higher resolutions, but I think we really need to get the molecular diffusion sorted before we do that. We would like to eventually do the deep atmosphere formulation with full Coriolis and variable gravity. Let's see, in the next year or two, we will be redoing the coupling to the IPE through ESMF, and we will also be starting to look into the development of new DA through JEDI. Another thing I want to say about this is we've started looking at longer integrations out to a year and doing examination of tidal features and comparison against what OBS we have up to, say, 80 kilometers. So with that, I'll stop and take any questions you may have. Thank you.
Any questions?
Couple of questions. For the thermodynamic equation, so you're solving for temperature or potential temperature?
Potential temperature.
So there is no option to solve. I mean, I remember the papers by Rashid that he was saying that in the upper atmosphere you need to solve for enthalpy or other forms of energy. So this is not part of things that you guys are exploring.
No, it's not.
Okay. And the second question is, what are you going to do for gravity wave drag in the thermosphere?
So we're working on tuning that right now. That's something Valery was working on, who's now at NASA, and I think Svetlana is taking that work over, but it's being worked on.
I think it's the transport of kappa, isn't it, that is sort of replacing the need to go to the CPT for the enthalpy, so you can keep the potential temperature, and you can do it by transporting the kappa, making that as a species, and then that ends up being equivalent, that's my understanding. Is that correct?
I think that's true, but Bill would know better than me. As it's currently done, yes.
Any other questions? Yeah.
So did you put in new sponge layer mechanisms at the model top to keep it stable? And a related question, do you see collapses of the pressure thickness when you remap? Or do you have smaller time steps even?
So we were actually able to take out a lot of the sponge mechanisms when we turned on the molecular diffusion, which I was happy about. We're not seeing collapse of the surfaces. However, we are currently testing using the time step from the GFS, even though we're running at much coarser resolution.
That could explain that.
Yeah, I think that's the case.
Last quick questions.
In terms of the full Coriolis, are you anticipating that to be a complicated change, or should that be relatively straightforward with the way the die core is already set up?
I don't expect anything to be trivial. Henry Zhuang drew out a plan for how to do these changes, but they were never implemented. It's strictly on paper at this point, and I hesitate to say it'll be easy.
Good. Any other quick questions? If not, thanks, Kevin. Great summary of what we're up to. So I'd now like to invite Hanli Liu. Hanli is at NCAR, and of course they have their own whole atmosphere model, the Wacom X. So he'll describe what that does and a little bit some of the results. Thanks, Hanli.
Thank you, Tim. My name is Hanli Liu. I'm one of the CIMA science co-lead at NCAR. And so today I'm going to very briefly describe our development of the Wacom X as part of the, or as the CIMA geospace component. And Mary Barth from the chemistry lab, she's the science lead for CIMA. And the other two co-leads are Adam Harrington from CGD and Bill Skamrock from AmCubed. So this is the outline of the talk. And so here, somehow it's got cut a little bit, but on the left of the plot is a schematic of the NCAR model ecosystem in the mid-2010s. Actually, it's not too different right now. But so you can see that we have, for the atmosphere modeling, we have a bunch of models that goes from very small local scales, hourly, small time scales, all the way to climate scales and global, and a lot of models in between. And around 2016, there was an NSF science or site visit, and one of the recommendations is to unify, come up with a unified system that we can run all these applications in that one unified system, and that's what CIMA's aim for. And I should point out, as let me see if I can get the pointer here. This maybe in the future I will talk with Mary to modify this, because our space weather applications we really want to go to from global scale probably to mesoscale, and at very short time scales, maybe on the order of hours to days for geomagnetic storm studies. So this should be expanded further this way. So we are now working on this from the left to the right. So here are we list the motivations for CIMA development. That's to enhance the frontier science simulations in climate, weather, atmosphere chemistry, and geospace, and also cross-discipline research. For the geospace aspect, one of the questions raised was, how do multi-scale processes and interactions affect geospace, atmosphere coupling, and space weather? And actually, all these questions came from the CIMA Vision workshop about 2 years ago. And I forgot to include a link to the CIMA website, which is just cima.ucar.edu, which has a link to the document, the vision document from that workshop. And these are, the additional benefits. They really, with that one model system, we try to engage a broad range of atmospheric and geospace scientists to collaborate and on various topics and maybe find mutually interesting and stimulating topics, and also maybe to fight over some things, hot debate. Something good will come out of that. And also for the management, it will be good for manage very efficiently the model development, the maintenance, and also the model support in long term. And also it will provide the opportunity to take advantage of the most advanced software development. I think Kevin just mentioned the CCPP, generic interfaces development, and also for take full advantage of the GPU development in upcoming architectures. And the goal, as I mentioned, is to come up with a single framework, a unifying framework for the atmosphere modeling system. And it should operate within the Earth system model like CSM. And here the schematic shows the interoperable components, physics, and also the dynamical core and data simulation. For the physics, according to your application, you can choose warp physics or chem physics, chemistry package, or ionosphere plasma and thermosphere modules. And for the die-core, we now have the option to work with AMPAS, the non-hydrostatic die-core, or FV cubed, as Kevin just mentioned, or the spectral element, which is still a hydrostatic die-core, which I will talk a bit more later. And specific for SEMA geospace, this is what we're working with. The purple circles are the components we're working with. We're working with the ionosphere plasma and thermosphere physics package. And currently it's still coupled to the die-core using the physics dynamics coupling, but CCPP is currently under development. And we're working with the SE die-core. And the atmosphere, the SEMA geospace can be coupled to the whole geospace, or not whole geospace model, but the MAGE, the multi-scale atmosphere geospace environment model, MAGE, which is the developed by the NASA Drive Center, CGS, to study storm time responses. And currently it's one-way coupled, so we get high latitude forcing from MAGE. And then the longer term, we want to have a two-way interaction between SEMA, WACAMX with MAGE. And actually, ultimately, at the end of the CGS project, we hope that the SEMA geospace will replace TI-GCM as the underlying atmosphere component. So these are our current development efforts. We are developing the high-resolution capability of WACAMX, and also the coupling I just mentioned, the WACAMX Gamera coupling, and also the non-hydrostatic die-core AMPAS in WACAM/WACAMX. So this is our very brief information about the high-resolution capability. We have developed the species-dependent spectral element die-core and solved on the cube sphere. Also, again, Kevin mentioned the molecular viscosity and diffusion in the horizontal direction, which is included in the current WACAMX in this die-core with subcycling capability. And also we as part of the SEMA project, we built a regrading scheme between physics mesh and geomagnetic grid, which is of course very key for supporting the interaction between the dynamo modules and transport energetics with physics. And for the high resolution, the resolution we're working with is 25 kilometer in the horizontal and 1/10 of scale height in the vertical. And here are a few kind of highlights from our studies so far using the high-resolution CIMA WACM-X. On the left, it shows the O2-N2 ratio. It's a zonal average O2-N2 ratio, which is a key quantity measuring the relative abundance of atomic species with respect to molecular species in the thermosphere. So WACM-X, regular resolution, and also previously TI-GCM, they all have this very gross overestimation of O2-N2 ratio. And now with the high-resolution simulation, it seems that what we can do better is the circulation, thermosphere circulation is better resolved because now at least partially the gravity wave forcing is accounted for in the high-resolution model. So as a result, we can get much better improved O2-N2 ratio. As you can see that the red is the kind of the ground truth is from GUVI measurement. So now we can do much better there. And on the upper right, we have this electron density structure. The color contour is from the regular resolution. The line contour is from the high resolution. So you can see that the EIA structure, equatorial ionization anomaly, both the vertical depth and the horizontal latitudinal distance between the two peaks are better resolved in the high resolution. And I'll see if I can play this. Okay, great. So this is another example. We use the high resolution to look at the whole atmosphere response to the Tonga volcano eruption. The lower layer is the surface pressure perturbation, and the upper layer is the TEC, the total electron content perturbation. And you can see that the Lamb wave modes are very well reproduced in the simulation, and the TEC result compare very well with various observations. And this is from the WACM-X Gamera coupling study. So here's a look at the density at 400 kilometers. It's a very key quantity for space weather study. And on the left are the high-resolution simulations, north and south, and on the right is the regular resolution. So two things you can see. One is that in the in the regular resolution case, the density, the neutral density, go to much higher values, go to more extreme values, indicating that it really lacks some adjustment process that should be there, or at least compared to the high resolution. High resolution model, which, as you can see, that doesn't the value is not extreme as the low resolution simulation. The other thing you can see is that let me see if you can see that. Yeah, on the screen you can see that from the high resolution, there are a lot of mesoscale structures now can be resolved during a storm. I forgot to mention this is during a storm. It's a storm time simulation. So at high latitude, now you see a lot of mesoscale structures in the high resolution, which is not there in the low res. And the third development is to adapt AMPAS for WACM and WACM-X. Here's some basic information about AMPAS. And what has been done, unfortunately the name got cut, is Sode Kamali is our ASP postdoc. She was leading this work. What she did is she adapted the AMPAS for WACM in the CIMA framework, and then she was did a intermodal comparison with WACM, same physics, but 3 dicores. And what's shown here are the wind climatology, the zonal wind from the 3 models, and also the color contour is the gravity wave parameterization. And you can see that she can get very similar wind climatology from all 3 models, which is a kind of verification of the model validity for AMPAS. So quick summary. So we're now developed toward the CIMA unified framework, and which will promote science advance. And also we had done already some simulations. I only showed the geospace simulations for high resolution to demonstrate that indeed with the CIMA high resolution we can have improved representation of the multi-scale processes. And just to quickly mention that there's a new science application or project selected to study sub-seasonal to seasonal scale sun to soil application. And they target 2 extreme weather events to look at the multi-scale and also coupling process and also the predictability during this, this event. Thank you.
Thanks, Hanley. Yeah, questions for Hanley?
You showed that all this CIMA thing has a coupler somewhere that currently is offline. How do you run the ionosphere time GCM? It's something that you run.
Oh, you mean with the MAGE?
Yeah,
the
or
MAGE
even
model.
in the earlier slide when you were showing the CIMA idea, there is a coupler, and you said that you can have a different component, the geophysical
Oh,
component.
I see. Oh, yeah, it will be just running just as CAM before. But now we have this, CIMA package that has all the nice, interoperability or all these nice components. But within CESM, it will be just run as, maybe that's why it's called CAM CIMA right now. It's just as an atmosphere component in CESM.
Oh, okay, got it.
And it's online. I mean, of course, you can use data ocean or data land to drive that.
Question? When you did the high and low resolution run, did you, for the low resolution run, do you have to add some eddy mixing of the species to get the right O to N2 ratio? I notice you're a little bit high on the O to N2. So you don't change that parameterization, or do you have a parameterization in the low resolution to start with for the eddy mixing that you had to change?
Yeah, that's a good question. So because the physics, for the current parameterization, the physics is not really valid in the thermosphere. It is Linsen-based, and the background viscosity is assumed to be very small. So we cannot really apply that parameterization. So that parameterization is turned off even in the coarse resolution. So that gravity wave parameterization stops at about 120 kilometers in the coarse resolution. And so it doesn't account for any gravity wave effects in the thermosphere right now. But for the high resolution, we also turned off all the gravity wave parameterization, but the resolved wave was doing some work to improve the circulation. Yeah.
Hanley, very nice. So the last but not least talk in the session is actually being presented virtually, remotely, and that'll be, Jonathan is going to tell us about some work to try to use the MET Plus validation package for some of the space weather parameters. So I'll hand it over to Jonathan. Oh, yeah, we're up there, good. Over to you, Jonathan.
Okay, thank you. Yes, can you hear me okay?
Yes, we can.
All right, I'm happy to be joining you guys from the highlands of Southwest Virginia today, where it's the warmest day of the year. It's only 85 degrees here, but it's as hot as it's been the whole summer. And so today I'm going to talk about the space weather verification work we've been doing with the Space Weather Prediction Center. And I want to acknowledge my team members. This project has been going on for the last 5 years or so. So there's quite a few people who've been involved from the SWIP side. And also on the NCAR side, we have Tara Jensen and the MET Plus team, which are not all listed here, but there's quite a few software developers and engineers, et cetera, who've helped out as well in this project. And the overview of this is that when we started working together 5 years ago, SWIP wanted to, they were interested in verification, and they wanted to get some capabilities, and they had heard about MET Plus. And so we started applying MET Plus to space weather, and then the pandemic hit, and they had some additional desires. They wanted to be able to run things on their laptop, and so this kind of informed the design of the system that we moved towards a platform-independent, container-based system that could be run on laptops or Linux workstations or Mac computers or a variety of different places. But we wanted to basically bring in the full capabilities of Met Plus so those could be brought to bear in space weather evaluation. And we didn't want to make them go to a lot of efforts to redo their model formats, et cetera. So we had to adapt some things with Met Plus to be able to read their data in the native data formats. And also we wanted to be able to allow them to conduct, interrogate their data, their verification data sets with MapViewer, and use other Python packages. So out of this has grown the resulting system. Now, some people in the space weather community may not have as much familiarity with MapPlus as a lot of the other attendees to this conference or workshop. So I want to spend a couple slides just explaining what MapPlus is and why we're using that. So MapPlus essentially is a highly configurable state-of-the-art verification system, which consists of a bunch of different tools that are quite efficient and extensible, and also Python wrappers, which can build up more complex workflows that use those tools and then pass the data downstream to analysis capabilities, et cetera. And this is really nice because it allows for very complex verification workflows to be simplified and codified for robustness and reproducibility, so that someone else can come along and take the same config file and the same data and they can get the same result. And this is very valuable because, say, 10, 15 years ago, there were a lot of different verification codes out there, and they weren't all necessarily speaking the same language. There's a lot of slight variations and whatnot. And having a system that's been well accepted across operational centers and forecasters and the universities and labs allows for this common verification language, so to speak. And as a result, the system's been building up over the last 10 to 15 years, and now there's a lot of training materials and support, which is very helpful. So it's basically a comprehensive verification tool set. And within here, there's different components. So I want to explain a little bit of what these are. There's the Met tools themselves, which are written in C++, and they run quite fast. And these can calculate over 100 traditional statistics and different diagnostic methods for point and graded data sets. And they produce output in both ASCII and CDF format that can then be involved downstream in the system. So in the case of NetCDF, you could just pass it off to your favorite plotting program and it generates some plots, or you can hand it over to the database, metdata.io, and this will compile all your results over many different runs, maybe even years worth of data, and then you can parse it and slice it and stratify it however you want. But the point is that this system is very flexible and allows for easy sharing of these workflows. So there's over 3,500 users around the world, and MetPlus is also now the core of the EMC verification system that's being used for the unified forecast system. Just a couple other notes about this. It's been used in a variety of timescales, ranging all the way from short-term weather all the way up to seasonal to sub-seasonal and almost to the climate scale. So that's something. It's also being used across a lot of different domains. So there's marine and cryosphere, as well as now space weather, tropical cyclones, extratropical cyclones, and other types of phenomena. So it's been expanding outward, and its capabilities have been expanding. And I think that's all I'll say about that slide. So what we did for SWPC, when I heard the requirements and what their desires were, I thought, well, let's try to do something a little bit more systematic. So the normal way that MetPlus would be running is that you would devise a use case, what's called a use case, which is a config file in MetPlus. And that defines the workflow that will call the Met tools and the downstream things that you want it to do. But instead, what we decided to do here was change it a little bit. And so we wanted to be able to run all the use cases at once, like you would perhaps want to do in a real-time system. So we defined all the use cases in one configuration file, and that makes it very easy to set up common things that are common between the use cases, and like, for instance, masking and whatnot. But it also allows you the flexibility to run everything in sequence. So that's kind of a nice thing. So it's kind of like a Python driver on top of MET+ that interacts with MET+ and calls the specific use cases. So in terms of complexity, it's not really any different than MET+. It's just running things in a different way. But it's also wrapping some capabilities to make things easier on the downstream end. So the diagram, I should note that the data sets don't actually flow into the driver, they flow into the specific tools that are being called. But here's a step here that you see the data sets come in. These include GLOTEC and WAM-IPE. Soon we'll have CTIP, and also there's MIT data. And this either can go directly into the tools if they're NetCDF or some format that MET recognizes, or you can write a Python embedding script. And that's a very powerful way to get data into MET, because MET doesn't have to know anything about your data format. You just write a Python script that can read it and put it in the frame that MET expects. And along the course, we've actually now started linking in additional other Python packages, which I'll talk more about in a minute. But once the MET tools are called, it generates a bunch of output and statistics, and then those can be passed into your database and through METViewer, and then you get your products and scorecards. So that's how the system runs. I want to show a few examples. The kind of the meat and butter of the system that has been used a lot by SWPC so far are these gridded comparisons. And so essentially what we're doing is comparing models with analyses or assimilative analyses like GLOTEC, where you're taking a bunch of observations and you want to see, okay, how well is the model, for instance, WAM-IPE, how well is it doing? So some of the key adaptations that were made for the space weather domain is, of course, to adapt it for the variables like total electron content. But also we spent a lot of effort creating some custom masks that would be useful for space weather. So here's a couple examples where the distance to ground stations, the ionospheric ground stations, either you want to make a mask of places that are near ground stations, or maybe you want to make a mask of places that are far from the ground stations. But there's an example. Up here, you can also see an example of azimuthal solar angle, so that you can stratify your results based on whether they're on the day side of the Earth or the night side or a certain solar angle. But there was another one, which was the quality flag, which is based on the number of radio occultation rays, for instance, from Cosmic or some other space weather vendors. And so I'll talk about that as well. So here's an example of a gridded comparison. These are for two space weather events in 2015. The first is a St. Patrick's Day event, and the second was another event in June that year. And what we've done is stratified the root mean square differences, I shouldn't say errors, but they're differences for a GLOTEC that used cosmic inputs versus a version GLOTEC without those cosmic inputs. And what we really wanted to do was see what is the effect of these varying quality flags. So the quality flags are varying in time based on how many rays are being taken. And so what you can see is that, yes, there are some differences. The TEC differences are relatively small between these, but what MET+ allows you to do, which is quite nice, is to stratify then by the quality flag. So after all that time varying information has been calculated, what you can see is that it turns out in data sparse regions where you have a low number of observations, if you add additional data point, it basically makes a significant difference. But if you already have a lot of data points, like a quality flag of 5, then it doesn't really make very much difference because you already have quite a bit. So SWPC used these capabilities to evaluate their real-time radio occultation data from vendors in the commercial weather data program. Another thing that we've set up is object-oriented comparisons. This is using MET's mode tool, and it's object-oriented in the sense that you can define your criteria. Like you can say, I want the area where TEC is over 35 units. And it uses fuzzy logic and basically will go in and circle and create objects based on where your blobs of 35 or more TEC units are. And then it will track those in time. And so this is really nice because then you can examine object attributes that you might not be able to do as easily, you wouldn't be able to do with a graded comparison, but you can measure things such as the distance, the centroid distance between the objects, their ratio of their areas, like if they're bigger or larger or smaller, the angle difference, how they're oriented, and the intensity ratio. And so one of the things that popped out really quickly when we started comparing WAM-IPE to GLOTEC, this is probably back in 2018 and 2019, is that WAM-IPE back then had a bit of a high bias. And so to basically get the objects to match up well, we had to increase the threshold by about 10 TEC units. So here's an example of what you can do with those object attributes. So we've taken those centroid differences in hourly, and we're, let's try to move this out of the way. What we're doing is comparing for forecast valid hour, so you can see through the day how these attributes are varying. And we're plotting basically box and whisker plots for different TEC unit thresholds. So you can see that for the low TEC thresholds, you have actually quite a bit of variation. You have some large differences that show up, and they're especially pronounced at different times of the day. So in this particular period, it's during the 0 to 12 UTC period. And the higher thresholds don't have nearly as much differences. So those are matching up quite a bit better in the models. So that was kind of an interesting result. Okay, and then another use case which we've developed more recently is to examine gradients. And gradients are of interest because when you have a sharp gradients of total electron content, you can get instability, which can cause these ionospheric irregularities. And these undulations can cause scintillation, which affects the radio communications. And so this new use case is computing these gradient magnitudes of TEC and comparing these. So on the left, we have the WAM-IPE TEC and the GLOTEC TEC, the 5 minutes offset because the models don't run at exactly the same time. And then we've used MetPy's geospatial gradient function. And this is a package that's been used for meteorological analysis, MetPy. They've done a lot of effort to make sure that the calculations are very precise using the map factors on the sphere. And so this was an example where we weren't readily finding any other good tools for computing this gradient, and it would be a pain to code this up and do it accurately just from scratch. So we were able to bring this in at the Python embedding stage and compute the gradients. So this is what this looks like. And if you just toggle back and say, oh, yeah, you would kind of expect the sharpest gradient is probably right here. And sure enough, there it is. So you can see that WAM-IPE has some sharper gradients than the GLOTEC is showing. And then here's a difference plot. So after these gradients are computed, of course, it's very easy to compute the difference in the tool. And then you can analyze to your heart's content afterwards, for a whole month or a day for different
30
events,
seconds left.
Okay. So the point is that this use case, we plan to keep developing and compare to point observations of scintillation. The last use case I'll mention is human forecasts of KP index. So we took SWPSI's data, which were in JSON format, and that wasn't something that could easily be read with MetPlus, but we adapted that and we were able to compute this. And you basically get contingency tables by lead time, which are plotted up here. So that's a nice result. So if you have any questions or information, please reach out. I've put up my information as well as Tara's and Terry's. Thank you very much.
Thanks, Jonathan. Sorry, we've run over a little bit. Do we have time for a question, or do you need to open up the... Oh, okay. Yeah, sorry, Jonathan, we're having to sort of open up the doors again. But thanks for your talk. And I'd like to, just close this session and thank the speakers once more for the excellent presentations and for keeping on time. So we had time for some discussion and questions. So thank you very much.